Hello, Algebra 2. This is a lecture on section 5.4, which is about factoring and also solving polynomial equations. This is going to be a very in-depth lecture, pretty complicated, so really work on staying focused and we should be able to get through this. The goal in section 5.4 is to be able to solve polynomial equations. Now, we have solved successfully quadratic equations where there, if we didn't have this first term, this 2x to the third here, we had this equation here. We have a ton of different ways to solve this equation, and even if it's a really complicated one, we have something called the quadratic formula, which will solve any quadratic. Now, it gets more complicated when we have a cubic, x to the third, or quartic, x to the fourth, or even more complicated than that. So what section 5.4 is about factoring these statements so that they are able to be easily solved. Now, a very intelligent question might be, well, Mr. Nyquist, is there such thing as the cubic formula to solve any cubic? And the answer is actually yes, there is something called the cubic formula. Unfortunately, this is what the cubic formula is. Cubics, here's a little hint. If it has an x to the third as its biggest exponent, the 3 indicates the number of solutions it has. So quadratics had 2, linear equations have 1, cubics have 3. Well, this is the math to get the first answer. This is the math to get the second answer. It's a pain, right? None of us are going to do this cubic formula. I've never even actually done the cubic formula to solve a cubic. Instead, what we're going to be doing is trying to factor it in hopes that the ones that Mr. Nyquist is giving us to answer at this point are factorable. So factoring is going to look a little bit different than in sections 4.3 and 4.4. Sometimes it's going to be a little bit more complicated, but one of the ideas that we need to know is that we're going to be trying to factor these things completely. And a polynomial is considered factored completely when it can't be factored anymore. This is to imply that there are going to be situations where you can factor them more than one time. When you have it factored completely, every polynomial will no longer be factorable. You cannot factor it any further. The first situation that we're going to talk about today is when you have a perfect square subtract a perfect square. Now, we've already factored x squared minus 121. I've never really shown you guys like the shortcut for it, but you guys have factored this. What you've done in the past is you've said, okay, what multiplies to negative 121? That adds to the middle term, which is 0. Well, what multiplies to negative 121 that adds to 0? That would be positive 11 and negative 11. So it would factor like x plus 11 and x minus 11. What I want to show you guys is that there's going to be a kind of a shortcut to factor this that can help us when we have to factor more complicated things like this one here. If you notice that the first term is a perfect square, remember our perfect squares are like 1, 4, 9, 16, 25, 5 squared, 4 squared, 3 squared, right? These are all the perfect squares. This is 1x squared. Well, what do you square to get 1x squared? You would square x. X times x is x squared. What do you square to get 121? 11. If you notice that you have a perfect square, subtract a perfect square, and it has to be subtracted, then you can take the square root of each one. Square root of x squared is x. Square root of 121 is 11. Add them and subtract them, and you have it factored. Okay? Or said differently, what do you square to get x squared? X. What do you square to get 121? 11. X plus 11, x minus 11 is how this would factor. That allows us to solve this. What makes this one 0 would be negative 11, and what makes this one 0 would be positive 11, and those would be our solutions. Notice the number of solutions, 2, negative 11, positive 11. Let's look at then a quartic. We've never ever factored a quartic before. We can actually do that using this trick. This is a perfect square, and so is 625. What do you square to get y to the fourth? You would actually square y squared. Y squared times y squared is y to the fourth. What do you square to get 625? That would be 25. You believe me? 25 times 25 is 625. So then to factor this, you would do y squared plus 25 and y squared minus 25 equals 0. Our goal is to solve this to figure out what actually makes it 0, and that was a big step in getting us there. This statement here could actually be factored again. This, once again, is a perfect square, subtract a perfect square. What do you square to get y squared? Y. What do you square to get 25? 5. So then using the same trick, we would have y squared plus 25, y plus 5, and y minus 5 equals 0. We know that this should have 4 solutions because it's y to the 4th. We actually know 2 of them right now. We know one of them is negative 5 because that makes this 0, and one of them is positive 5 because that makes this one 0. Once we have everything degree 2 or less, like this one's degree 1 here, this one's degree 1, and this one's degree 2 here, if we solve this quadratic, we now know the other 2 solutions, right? If I knew what makes this one 0, I would have the 2 solutions from this, one solution from this one, negative 5, and one solution from this one, positive 5. So finding the solution is a little bit difficult, but I could set it equal to 0 and find it. And actually, this one isn't too bad. I could use the quadratic formula to solve any quadratic, but this only has a y squared, doesn't have a plain y. So I can solve this using roots. Y squared is equal to negative 25. Take the square root of both sides. Whenever I take the square root of both sides, I get a plus or minus. And the square root of negative 25 is 5i. Remember, taking a square root of a negative creates an I, and taking the square root of 25 is just 5. So there are 4 solutions to this problem. Positive 5i, negative 5i, and negative 5 and positive 5. We've never been able to factor quartic before, something of degree 4. We've never been able to solve a quartic before. But now we solved our quartic, negative 5, positive 5, 5i, and negative 5i. If I asked a different question here, if I only asked you to factor it completely, that would be this solution here. This is the point where I wasn't able to factor anything more. This trick, remember, only works when it's a perfect square, subtract a perfect square. Here's a perfect square plus a perfect square, not factorable ever. We factored this statement again and got our solution. Let's look at a second type of trying to factor something completely. This says when all terms have something in common, factor out that common thing, that greatest common factor. So this is going to show up a lot. In this problem here, you can see that all of our terms, x cubed, 2x squared, and negative 15x, do have something in common. And that common factor in this problem is just the term x, the variable x. So what we can do is we can undo the distributive property with x, with the greatest common factor. So if I take an x out of everything, right here would be an x squared. This one would be a plus 2x. And right here, I would have subtract 15. I would then look to factor anything that I could again. And this statement actually could be factored relatively easily. This is your traditional factoring. What multiplies to negative 15? We have 1 and 15 and 3 and 5. And how would these add to positive 2? Well, if it was positive 5 and negative 3, these add to positive 2 and multiply to negative 15. So factored completely would look like this. If my question was to factor it completely, right, then this would have been the answer. There would have been no equals 0 here. It just would have been, hey, this is it factored. But I can take it a step further. I can actually solve. I can tell you what values for x would make this a true statement. I just have to figure out what makes this one 0. That's just 0. If I plug in 0, this is 0. 3 for this one, and negative 5 would make this one 0. There's my solutions. Very easy to check by plugging in, making sure that they do actually give me 0 here at the beginning. If I plug in 0, 0, and 0, this is everything is 0. It does work. If I plug in 3, 3 squared is 27. If I plug in 3 here, I would have to do the exponent first because of order of operations. 3 squared is 9, and 9 times 2 is 18. And then this one would be minus 45. Because 15 times 3 is 45. 27 plus 18 is 45, and 45 minus 45 is 0. It worked. Let's move on and try this one. They do have something in common. in this problem as well, right? That's my goal in this type, this variety, is to factor out the greatest common factor. Well, 2 and 18 actually have a common factor of 2 as well. I'm going to factor that out. That's going to make my life a little bit easier. In addition to the 2, though, I can actually factor out a y cubed. This one has 5 y's with it, and this one has 3 y's. In common, they have 3 y's. I can factor out that 2y cubed. So if I take out a 2y cubed here, what would go in the parentheses would be y squared. 2y cubed times y squared, right? If I redid the distributive property, would give me 2y to the 5th. And this one here would be minus 9. Now I have something that is factorable. Y squared minus 9 is factorable using stuff from this slide over here, right? I have a perfect square, subtract a perfect square. What do I square to get y squared? Y. What do I square to get 9? 3. So 2y cubed in parentheses y plus 3 in parentheses y minus 3 equals 0. Now, if my goal was to factor it completely, I have done so. But if my goal was to solve it, which this one appears to be since it's set equal to 0, I would have to say, what makes the parentheses 0? 3, negative 3. And what would make this y 0? Well, plugging in 0 would make the 2y cubed 0. Now, it would be a very intelligent question if you said, hey, Mr. Nyquist, you said it should have the number of solutions equal to the degree. So it should have 5 solutions, but you only came up with 3. Why did you only come up with 3 solutions? I've got an answer for you. Y cubed, stick with me here, y cubed is the same as y times y times y. So this is not an incorrect way to write this statement, right? 2y to the third, 2y, y plus 3, y minus 3. So if I were to solve this, 3 makes this one 0. Negative 3 makes this one 0. And then what makes this y 0? Well, 0. What makes this y 0? 0. What makes this y 0? 0. So, in a sense, 0 is a solution 3 times. Negative 3 is a solution, and 3 is a solution. These are the 5 solutions to this 5th degree polynomial. We don't really need to write 0 multiple times. I do think it shows up in like an extra credit question. I say, tell me every one of the zeros, including multiplicity, which is what this is, right? It's a solution multiple times. But I would accept this as your answer to solving this polynomial. So let's go ahead and try this one. This is a good time to pause, see if you're able to come up with this solution. Right away, I noticed that they do have something in common. Not only do they have a 4 in common, right? 4 is a factor of 4, 16, and 16, but they also have a z squared in common. If I were to factor out a 4z squared, I would be left with z squared minus 4z plus 4. From here, I would look to factor this statement, z squared minus 4z plus 4. This is your normal factoring. Okay, what multiplies to positive 4 that adds to negative 4? Well, the factors of 4 are 1 and 4 and 2 and 2. Would any of these add to negative 4? Yeah, negative 2 and negative 2 would, right? So I'd have 4z squared, z minus 2, and z minus 2. If I were to ask you to factor this completely, I would actually prefer it to be written like this, 4z squared, and then z minus 2 squared. You buy that, right? Because these are just the same thing being multiplied by itself. So I could write it as 4z squared, z minus 2 squared. However, if we're trying to solve this, the answers would be 2 here, and I guess 2 there. I don't need to write it twice, but I could. And then 0 here. So if I was writing all of the zeros, 0, 0, because z squared. So remember, it could be written like this. 0, 0, 2, and 2. Or even 0 and 2, I would accept. The third and final way of factoring that I'm going to talk about in this lecture is something that I kind of refer to as even half none. That's definitely not something that you're going to find in the textbook as a way to refer to this, but it's what I call this type of factoring. What I want you to do is I want you to factor these statements just like you would in section 4.3 or 4.4. 4.3 is your basic factoring, x squared factoring. Okay, we did it right over just here. 4.4 is your box method factoring, and we're going to do that in this problem here. Remember, 4.4 is when you have ax squared plus bx plus c, when you have a number in front of the x squared. What I mean by even, half, none is if your exponents, your biggest exponent is an even exponent, your next exponent is half of that exponent, and then your last term doesn't have an exponent at all. If that is the scenario we're in, I want you to attempt this even, half, none factoring. And in a sense, what you're doing is you're factoring it as if it were 2x squared plus 7x minus 30, but the exponents are going to be a little bit different. Basically, if you were to factor this statement, this, because there's a number in front of the x to the 6th, the first term, that tells you it's going to need the box method. And you should be able to answer this question just like you would have in previous sections, in section 4.4. The first term goes in the first box, 2x to the 6th. The last term goes in the last box, negative 30. And then you multiply 2 and negative 30 and you get negative 60. And you're looking for factors of negative 60 that get you to positive 7, the middle term, right? This is not new. This is just like section 4.4. The factors of 60 would be 1 and 60, 2 and 30, 3 and 20, 4 and 15, 5 and 12. Well, which one of these could, and then we also have 6 and 10. Which one of these could get you to positive 7? Well, if it was positive 12, negative 5, that would get you to positive 7. So 12 and negative 5 are going to go in these two boxes, but notice I don't want it to add up to 7x. I want it to be 7x cubed. So both this one and this one are going to need x cubes now because that's what our middle term is. Just like we did in section 4.4, locate the greatest common factor of the top two boxes. What is common between 2x to the 6th and 12x to the 3rd? Hopefully you are screaming 2x to the 3rd. 2 is the greatest common factor of 2 and 12. And if one has 6 x's and one has 3 x's, what they have in common is 3 x's. From here, you fill this out like a multiplication table. 2x to the 3rd times the thing that goes here is 2x to the 6th. That would be just x to the 3rd. Over here, this one would be 2x cubed times this, whatever happens to be, is 12x to the 3rd. That would be 6. Whatever goes here would be x to the 3rd times what is negative 5x to the 3rd, simply a negative 5. And then as our check, do 6 and negative 5 multiply to negative 30? They definitely do. So my factors are this in parentheses and this one in parentheses. Answer. That's it factored completely. We actually don't have a way to solve this one or this one at this point, right? If we had the cubic formula, that huge annoying thing at the beginning, we could solve this, but we actually don't have a way to right now. So this would be our factored solution, and this would be not solvable if I had asked you to solve this. So let's go ahead and try this one. If you wanted to use the box method, that would take you to the right answer. But notice that this one doesn't have a number in front of x to the 4th. It does fit this pattern, even exponent, half of that exponent, and then none. But we can just factor this using the method from 4.3. We can just list the factors of negative 40, 1 and 40, 2 and 20, 3 doesn't, 4 and 10, and 5 and 8. Well, which of these factor pairs would get you to negative 3? Well, if you had negative 8 and positive 5, that would get you to negative 3, and it also multiplies to negative 40. So factored, this would be, you would think maybe it would be x plus 5 and x minus 8. But we want it to we want the first times first to multiply to x to the fourth. So it's going to actually be x squared plus 5 and x squared minus 8. If you were curious to see how this works, go ahead and FOIL this. You should get right back to where you start. We can actually do that real quick. X squared times x squared is x to the fourth. That worked. Outside times outside gives you minus 8x squared, and inside times inside gives you plus 5x squared. Combine them, negative 3x squared, and then 5 times negative 8 is negative 40. Now this one is set equal to 0, and so that means that I am expecting you to solve them. Because both of them have x squareds but no x, we can just set them equal to 0 and solve them. Subtract 5, you would get x squared is equal to negative 5. Take the square root of both sides, you would have x is equal to, remember when you take the square root of both sides, you get a plus or minus, and the square root of negative 5 would be I root 5. Remember, taking the square root of a negative just creates an I, and square root of 5 cannot be simplified. Then we have to solve this one here, x squared minus 8. So set it equal to 0 and solve it. Add 8 to both sides, x squared equals 8. Take the square root of both sides. So we'd have x is equal to plus or minus the square root of 8. But the square root of 8 is something that can be simplified. Remember, it has a perfect square factor, and that perfect square factor is 4. So it would be x is equal to, we'd have plus or minus root 4, root 2. Square root of 4 can be simplified, plus or minus 2 root 2. So my 4 answers are I root 5, negative I root 5, 2 root 2, and negative 2 root 2. This is going to be our last slide in this part of the lecture. I would say go ahead and pause it here and try to work through these, see how you do, and then we can come back to, or then push play when you're ready and we can go over it together. With this first problem, what I would want you to notice is that this is a perfect square, subtract a perfect square. What do you square to get the first one? It would be 4x squared, and you square 9 to get 81. And the pattern here says to add these and subtract them in parentheses, and that would be a factorization of it. That would be you factoring it. Now, once again, this is still factorable. This is a perfect square minus a perfect square again. So you'd have to say, what do you square to get 4x squared? That would be 2x. And what do you square to get 9? That would be 3. And add those and subtract those, and that would be you factoring it. So this answer here would be negative 3 halves, because you'd set it equal to 0. 2x plus 3 equals 0, and solve it. And setting this one equal to 0 would be 2x minus 3 equals 0, and solve it. You'd add 3 and divide by 2, so that would be positive 3 halves. You might think that this is factorable, but perfect squares plus perfect squares are never factorable. You would always get stuck trying to do that. So instead, you would have to solve it some other way. And actually, we can just set this equal to 0. Once again, we don't have a plain x term, so we can just set it equal to 0. And solve it. You would subtract 9, divide by 4. Take the square root of both sides. Whenever you take the square root of both sides, you're going to get a plus or minus. And then we have a rule that says we can't have a square root of a fraction. So what you'd actually do is you take the square root of negative 9 and the square root of 4. The square root of negative 9 is actually 3i, and the square root of 4 is 2, giving you plus or minus 3i over 2, and the other solutions of negative 3 halves and positive 3 halves. that's a tough problem with solving this statement here. I think that's pretty tough. More likely, I would ask you to get to here on this question. This one, I'm only asking you to factor it. Let's go ahead and try to do that. Right away, I notice that they all have something in common. They all have a 2p squared in common. So I'm going to factor that out. That's the greatest common factor. If I took out a 2p squared out of 2p to the 8th, the 2's would cancel, and I would be left with p to the 6th. If I took out a 2p squared out of 10p to the 5th, remember I'm undoing the distributive property, so I could think of it as what multiplies. That would be 5p to the 3rd. And this last one, 2p squared times what would be 12p squared? That would be positive 6. Hopefully you've recognized what the type of factoring that we would do from here. This is the even, half, none rule. So in a sense, you factor it just like you would have in section 4.3. This 2p squared is just going to tag along out front. But here you'd be asking what multiplies to 6 that adds to 5. And actually both of them kind of do, right? 1 and 6 could add to 5 if the 1 was negative and the 6 was positive. And 2 and 3 would add to 5 if they were both positive. So which one works? Well, negative 1 and 6 doesn't actually multiply to 6. Remember, it has to multiply to the last and add to the middle. So it's not this one. It's going to be plus 2 and plus 3. So in parentheses here, we'd have still that 2p squared taken along. And then in parentheses here, we'd have p in plus 2 and p in plus 3. Only I want the first times first to multiply to p to the 6th. So what actually goes here is a p to the 3rd and a p to the 3rd. So if my question was to factor this statement completely, your answer would be this. I know this is a tough section, you guys. Make sure that you are practicing this on the worksheet that I have on Schoology with the answer key. It's going to be pivotal that you're practicing this. Let me know if you guys have any questions.